In the last video, I introduced you to the first of 5 thread pool executor services that Java offers. This was the fixed thread pool. This service created a fixed number of threads in its pool and never increased or decreased them. There was no dependency on the number of tasks, in other words. I'm going to again use the executors project to continue with this discussion, introducing you to some other thread pools. I've got the code open to the main class. In this class, I'll add a new method. This method will sum up a series of numbers. The task will pass the starting number, the ending number, the delta, or the amount each iteration will increase by, and the colour the thread should be printed out in as a string here. This will be a private static method and it won't return anything. I'll set NC reset to the thread colour variable. In the try block, I'll assign the value of colour string to thread colour. I'll catch an illegal argument exception if the user passes a bad colour, and I'll just ignore it. I'll assign the thread colour to a string variable, colour. I'm going to have an endsum, and I'll set that to 0. I'll use a regular for loop to loop from start to end, summing up the delta values. Finally, I'll print out the colour, the current thread, the colour string, and the sum. I'll once again rename the current main method because I do think it will help you to keep these multiple versions around to compare the different executors. I'll rename that method to fixed main and create a new main, so PSVM. I'll use type inference and again call my variable multi-executor, but this time I'll call new cached thread pool with no arguments at all. I'll now wrap this code in a try block. I can execute a task as a lambda expression using the execute method. In this case, I'll pass parameters to the lambda rather than use a method reference. So first, I want to sum all the numbers from 1 to 10, incrementing by 1 each time, and print that in red. For the next task, I'll start at 10 and go to 100, incrementing by 10, so this task will sum 10, 20, 30 and so on, and print that sum in blue. Lastly, I'll sum the even numbers between 2 and 20, printing that amount in green. I'll include a finally clause which is considered best practice. This clause will always shut down the executor. Now that you understand thread pools a little bit, you might understand why the shutdown method is necessary. A thread pool will stay in existence until something tells it to stop running, and that's exactly what the shutdown method does. Okay, so I'll run this code. I'll get 3 statements back in no specific order. Red will give me a sum of 55, green will give me 110, and blue will be 550. You can see I have 3 distinct thread names, so this pool had 3 threads executing, even though I never specified a thread count for this executor service. I'll copy my 3 execute statements and paste a copy right below the last one here. I'll change the colours for each of these new statements, but just keep the lambda the same. I'll change red to yellow, blue to cyan, and green to purple. I'll run this code again. Now I should see 6 statements in different colours, and again there's no real order. Notice the thread names, they're all still unique, so my thread pool is growing as my tasks increase. Before I shut down, I'll hang out for a second, then I'll execute a few more tasks. To do this, I'll call sleep before the shutdown method. I'll do it with the time unit seconds here. I'll sleep for 1 second. I'll print out a message that the new task will be executed. I'll use an enhanced for loop to loop through some colours while I call the sum method. If I run this code, my first 6 tasks will complete. I'll see a statement that says, next 4 tasks will get executed. Then I'll see the statements for the final 4. Notice the thread names used in the second set of 4 tasks. The pool appears to be reusing existing threads at this point in the pool. I say appears because I don't really know for sure, since this is all managed for me behind the scenes. I'll talk about how the cached thread pool creates and destroys threads in just a minute. First though, I'll add 3 more colours to this array. I'll rerun this. You'll notice that I now have 7 uniquely named threads, so again, this thread pool is growing. I'm going to come up a little bit here in my code to the first statement in the main method. I'll Control-click on the executor's method there, so on the method new cache thread pool. You can see this is creating something called a new thread pool executor. What I want you to see though is the arguments and the parameter names which IntelliJ is showing us in lay hints. There's a core pool size, so in this case it starts at 0. This means the pool won't create threads when it's instantiated. The maximum pool size is the max value of integer, and we know by now that's 2.14 billion something. That's a lot of threads. Next there's a keep alive time as well as time unit, and here we can see it's 60 seconds. This means after 60 seconds, cached threads will be dropped. Getting back to the main class's main method, I'll delete this last bit of code. I'm also going to delete the last 3 of the 6 statements above this. In addition to the execute method, which I've been using, these classes have a submit method. I'll change my code to call submit instead of execute in each of these cases. This code compiles and I can run it. I get 3 threads completing just as if I had used the execute method. So what's the difference here? For this particular example, execute and submit do the same thing. The method I'm executing, the sum method, doesn't return a value from its method, so the submit method knows it's executing a runnable. The submit method though, unlike the execute method, can also run a callable. What's the difference between runnable and callable? Significantly, callable returns a value. This means you can get data back from your running threads. You can have 2 ways of communication when using submit. On this slide, I'm showing you the method signatures for both the execute and submit methods. There is only a single execute method, and it takes a runnable and returns no value. The submit method has 3 overloaded versions. Notice that in all cases, each returns a result, an instance of something called a future. The submit method I just demonstrated in my code was an example of the first submit method which executed a runnable. In this case, simply ignored any result coming back. I'll be demonstrating the differences between each of these shortly. First, let's talk about the future. A future represents a result of an asynchronous computation. It's a generic type, a placeholder for a result instance. It has methods that cancel the task, retrieve the result, or check if the computation was completed or cancelled. The get method returns the result, but you can only call this get method when the computation is complete, otherwise the call will block until it does complete. The overloaded version of the get method allows you to specify a wait time rather than blocking. Let's examine this in some code. First, I'll change my sum method. I'll continue to print the result, but I also want to return the sum from the method. So I'll return an int. If I go back to the main method, notice my code still compiles. The submit method doesn't really care if I do anything with the result of its call. If I hover over one of the submits, I can see I'm calling a different overloaded version of submit now, which takes a callable as its argument. In my code, I'll use type inference and assign each of the submit calls to a variable. Notice IntelliJ's inlay hints. In each case, the result is a future with a type parameter of integer. I'll print each result by calling the get method that lets me specify a timeout. I'll wrap all of these calls in a single try catch and just catch any exception, since there's a variety of exception types that could get thrown here. In each case, I'll invoke the get method on each task's result with 500 milliseconds, starting with the result of the red task. I'll do the same for the result of the blue task as well as the green task. In this case, I'll catch any exception using the more generic exception class, and I'll just rethrow the exception if I did get one. Running that code, I should be able to see just the results, in other words, just the sum of each task printed out. The future is a way for a task to communicate its result back to the calling code. Up until now, I've only executed a task individually using either the submit or the execute method. The executor service implementations have a method named invokeAll. I'll again rename the main method to cached main and create a new main method. I'll copy the first statement from cached main as well as the try statement and paste it in my new main method. I'll do the same as well for the finally clause. Now, instead of individually executing tasks, I'll first set up a list of callable tasks. I'll create a list of callables which will return integers. My tasks will be the same as I used previously. I'll just set them all up here individually, so main.sum, and this will sum 1 through 10, printing it in red. The blue task sums numbers by 10, starting at 10 and up to, and including 100. Green sums even numbers between 2 and 20, same as before. Next, I'll add code in my try block. I'll call invokeAll on my multi-executor instance. This method takes a collection of callables so I can pass my task list. From the inner hint, we can see the inferred type of the result. It's a list of futures which will wrap integer value results. I'll loop through the results, printing out the result of each callable, waiting up to half a second before retrieving it. I'm getting 2 errors now, but if I hover over get, it's shown that 3 exceptions need to be handled. Instead of getting IntelliJ to generate a catch block for each exception, I'll just create one multi-exception catch for all 3 exceptions. I'll catch interrupted exception, timeout exception, and execution exception. If I get any of these, I'll rethrow it as a runtime exception. Running this code, I get the same results as before when I called submit on each task individually. The difference here is I was able to create a collection of tasks up front or before I needed them, then pass them all to the executor services invokeAll method. And I can get the results in a single collection rather than having to get each result individually. There's another method that's a bit different called invokeAny. Let's look at that real quick. I'll change invokeAll to invokeAny in my code. Notice that I've got errors now, and that's because my variable results isn't a list coming back from this method, it's actually just single value. And the result's not a future, it's just an integer. I'll comment out the for loop and remove the call to get, and instead just print the integer out. I also don't need to catch a timeout exception, so I'll remove that from my multi-exception catch. I'll run this and see what I get. I'll run it a couple of times. Notice I get messages that all threads were run, but results for only one of those, and it appears to be arbitrary. The result we get back is actually the result from the task that completes first. It returns only that one completed task's results. Even though, in our example, we can clearly see all our tasks were executed, this isn't necessarily always the case when you use invokeAny. When would you want to use invokeAny versus invokeAll? For invokeAny, only one task is guaranteed to run, and that's the first one to complete. For invokeAll, all tasks are guaranteed to be executed. For invokeAny, remember our result wasn't a future. In this example, it was simply an integer and was the result of the first task to complete. For invokeAll, we got a list of the results of all the tasks that completed, which were all the tasks we passed to that method. What's a good use case for invokeAny? Imagine trying to get a result back from 3 possible web servers available to answer some kind of question, perhaps Google, Bard, and ChatGPT, for example. The first response is all you need, so you fire off 3 tasks and return the first and fastest result to your client. This is quite a different use case than one where you want your application to troll multiple websites and then compile a list of answers from all 3, for example, which would benefit the invokeAll model. Okay, so I think this is a good place to end this video. Coming up, I'll cover a couple of other classes for managing threads, but first I think it's time for a challenge. I'll see you in the next video for that.